Oh yeah, she's wrong. In front of like all these people.
You're gonna be on YouTube. You're gonna be on YouTube. It's recording.
Oh, I'm going to get a job in my high school anyway at this point. The principal called me out the next day, like after meeting with like.
My district seems to be giving preference to my students. One of my students asked for help, and he said, "You know what? If you ever need a job, Randolph, yep." Okay, so we're now on the next, I think he's calling it sections, but it's chapter 3, the factorization. And this is actually something everybody should be really familiar with. It's that thing where you take a number and you break it down into its prime factorization. So this is what this section is about. It's one of the most important concepts in math, actually. And when I've watched students, you know, one of the things you see students all the way up, you think, gosh, I wish I could have started over with them and shown them how to break things up with prime numbers and how that is important when you're combining fractions and how that relates to when you're doing algebraic fractions and how you build up in this way. And I finally got to do that experiment. I had children. So I show my children when they're very small how to break up things into the primes. And when it comes time to add fractions, life becomes easy. Breaking up under a radical, life is very easy for them because it's the same concept coming back. It is the breakdown of the entire set of integers. And that's why the name of this theorem that we're going to talk about today is called the fundamental theorem of arithmetic. So you're taking a step back now. Fundamental theorem of calculus, and now you're going back and saying fundamental theorem of arithmetic. All right, so you have, in this book, now he absolves himself by saying that whenever I write a lowercase letter, it's always going to mean positive integers. So he writes that at the beginning of this section. P is a prime if it is a number that's only divisible by itself and 1. N is called composite if it's not prime. So every positive integer is divisible by a prime. Here's the rephrase. The top is every positive integer is divisible by a prime. You can always state that as an if-then statement. So whenever they say every positive integer, you can say let n be a positive integer. If n is a positive integer, then n is divisible by a prime number. That's how you can convert it to an if-then statement. So I'm going to do this proof because it's a concept that you see again in all your proof writing classes. If you have n is a positive integer and you want to show that it's divisible by a prime number, one of the things you can do is create a set which contains all of its divisors. And the idea is to show that one of the elements from that set is going to be prime. So I'm going to let S be the set of integers, j, between 1 and n, so it's not 1 and it's not n itself. And I'm going to show that j is divisible by, I'm going to show that one of these numbers in here is going to be prime. Well, I have two cases. One case is that there's nothing in there. Well, if there's nothing in that set, what does that mean about the number n? It's prime. It has no other divisors than itself and 1. If S is empty, then n is prime by definition. What if it's not empty? Well, if S is not empty, then S has to have a smallest element. This is called the well-ordering principle, which I don't think he's talked about in here, but you talk about this in a set theory class, and sometimes at the beginning of modern algebra, they talk about the well-ordering principle. So every finite set must have a smallest element. So I'm going to let P, leading my reader here, that's going to be my candidate for the prime, be the minimum number in this set S. I claim that P is prime. Suppose on the contrary, so I'm going to do a contradiction proof. It's either prime or not. There's only two choices. Suppose on the contrary that P did have a divisor. Let C be that divisor. Then C divides n as well. How do I know that? Well, I can just write down the equations and show it. That if C divides P, then C has to divide n. But that's a problem because C has got to be smaller than n. C's got to be smaller than n because it's not prime. It's in some other number that's smaller than P. and bigger than 1, so that's impossible because p was already the minimum, the smallest thing I could have chosen from that set S. So now I found out something even smaller that divides n. So that means that our assumption was false, and p has a positive divisor, that p has a positive divisor is false, and the only divisors of p must be p and 1. That's the definition of p being prime. That means n's divisible by a prime in all cases, and that proves that exactly that every composite number or every integer can be expressed has a divisor that's prime.